today learn about properties of bond types. We have learned different types of bonds. Ionic bonds, covalent bonds. Something we have not discussed yet is called coordinate covalent bond, and I will talk about it on Wednesday. But anyway, properties of bond types: ionic bonds, covalent bonds, metallic bonds, and allotropes. Allotropes is not really a bond, it's different forms. It's kind of one you can say because allotropes are different forms of the same element because atoms are bonded differently and the silicon-based structures. So ionic bonds, of course, are the strongest bonds, or very, very, very strong bonds because of the cation and the anion. So they have high melting and boiling points because those different ions are holding each other very tightly. So ionic bonds have high melting boiling points. They're very hard, brittle crystals, and they have very specific crystalline structures. Lattice structure we call it. They do not conduct electricity in solid state. Why they do not conduct electricity in solid state? Because each atom is bonded to another atom, and it's held at a particular place. So since they're held to their positions, it's very they don't move. Do you understand what I'm saying here? That each atom is bonded to another atom, and they are specifically placed at a position. They don't move around. And to conduct electricity, they have to move around and float around. So when they're in solid state, they do not conduct electricity. But if you melt them, if they're molten, or if they're dissolved in water, where they turn into ions, dissociation happens. That is when they are good conductors of electricity. So they're excellent conductors in liquid and aqueous state. Aqueous, of course, means dissolved in water. They're also called electrolytes because they're good conductors of electricity when they are melted or when they are dissolved in water. So this is what we want to know about ionic compounds. They have a very specific crystalline structure. We call it a lattice structure. A lattice is a three-dimensional structure. We also need to know what is the definition of a lattice. It's a 3D shaped structure where each atom is bonded to a certain number of other atoms. Then we can talk about metallic bonds. Well, of course, the name specifies this is the bonds between metals. How metals are holding each other together. Because ionic bond, we have learned about ionic, which is what? Metals and non-metals. We have learned about covalent, which is what? Non-metals and non-metals. So this is what you have learned to this day. The third type today is the metallic bonds. Metallic bonds are attraction of metallic cations for the delocalized electrons. So what happens is, I don't know if it is clear or not, but there are positive, this is the nucleus of each metal atom. Okay, and that nucleus, if you see, is surrounded by electrons, the negatively charged electrons. So these negatively charged electrons are delocalized, means they're floating around. Like sodium has one valence electron, right? Chlorine has not chlorine. Maybe another atom, zinc, has two valence electrons, or iron has 2 or 3 valence. So they're all floating around. So one electron of sodium within its metal is kind of floating around. It will not stick to just this one sodium atom. It will float around. Electrons C model creates a delocalized electrons because they have a very low ionization energy. Metals have low ionization energy. I can easily delocalize those valence electrons. So you need to also add that in. Now, why we have delocalized electrons in metals? Because they have low ionization energy. It is very easy to move them around. So properties of metallic bonds. They're very strong bonds, especially transition metals, because they have multiple valence electrons. So more electrons you have, the stronger the strength, the stronger the bond will be. They have high boiling points because they are strongly bonded together. Average to high melting points because of electron C. They conduct electricity in solid state. So you see, this is what makes them different from ionic compounds. Ionic bonds do not conduct electricity in solid state. Metallic bonds do. Metals do conduct electricity in solid state because of those delocalized electrons. They're malleable. What makes them malleable? Why I can hammer them into sheets. Malleable means I can hammer it into thin sheet because those cations can float on each other. Okay? So that makes them malleable and ductile, very shiny. Strength of metallic bond depends on three factors. So whatever the properties here that we're talking about, they have strong melting boiling points, they're malleable, they conduct electricity. These are all the properties of metallic bonds. But what these properties depend on? These properties depend on the number of valence electrons that can be delocalized. Like for sodium, I can only delocalize one electron. Okay, for calcium, I could delocalize 2 electrons. For iron, I could go up to 3. For lead, I could probably go up to 4 and 6. You get my point? So more electrons I have that I can delocalize because of their low ionization energy, the stronger the bond will be. The charge of the metal ion, like sodium has positive 1, magnesium has positive 2, aluminum has positive 3. So how strong the nucleus is that is connected with those delocalized electrons. It's down here. The ionic radius of the metallic atom. The larger the radius is, the stronger the bond will be because it's easier for me to delocalize it. So these are the properties or the factors that determine those properties.
You want a larger radius because that's easier?
Yeah, it's easier to delocalize it. There are different kinds of alloys of metal. Okay, at allotropes of solids we will covalent compound we will learn. But metal alloys, we have learned about this before. Alloy is basically a mixture of solids. Their different metals are mixed together. Because metals are very soft. Because, again, why are they soft? Because they have those mobility of the delocalized electrons. I can shape them any way I want it. But if I want to make it harder, like even gold, the jewelry that we make, or the silver, if I take 100% pure gold, I cannot really shape it into any kind of necklace or a chain or a ring because it will not hold it in its place. It's very soft. So I have to make it a bit harder to hold it in its shape. So we can make the metals harder by placing other elements in it. And those homogeneous mixture. So alloy is basically a homogeneous mixture of different solids, okay, where they are given a very high pressure and temperature, and they are homogenized in a way that it is not easy for us to separate them mechanically. Okay, for example, brass. Brass is the combination of copper and zinc. So there are different kinds of alloys. You have substitutional alloys and then interstitial alloys. Substitutional alloys means that I have, let's say, copper, or I have zinc, and I will replace some of the zinc atoms with copper atoms. Okay? So out of this is all zinc. This is the sheet of zinc. Then I will replace some of the atoms out of the sheet of zinc with copper atoms. These different charges will hold each other strongly and give them the new strength. So different kind of metal alloys. Alloy, first of all, is a mixture of different atoms by different solids. Substitutional alloys where you're replacing the whole atom. And the next is called interstitial alloys. This is really steepness. There is all iron, but you have the empty spaces between the iron atoms, and those empty spaces are filled with carbon to give you different strength. Okay, this is called interstitial alloy. So it's right here, interstitial alloy. Interstices mean holes. There are holes in the iron which are filled by carbon. So steel is an example of iron and carbon. So different kind of alloys. First, so we learned about metallic bonding. Metallic bond is made of cations of metals with electrostatic force between cations of metals and the electron C around it. That electron C is formed by delocalization of valence electrons. So this is about ionic and metallic bonds. The next we move on to covalent bonds. There are different types of covalent bonds. When we talk about covalent compounds, it could be a very crystalline structures. You or solid, or that would be amorphous. Crystalline, of course, tells you very structured arrangement, a three-dimensional arrangement. Amorphous is a very disordered arrangement. So, let's talk about, I'll come back to that one. Let's talk about carbon allotropes. First of all, allotrope, as I said, is the atoms of the same element, but that have different physical and chemical properties just because the atoms are bonded differently. Carbon is very unique. It bonds to other atoms of carbon in many unique different ways. It can bond to two atoms, it can bond to three, it can bond to four, it can bond to, up to different ways. And that gives us a very unique nature. So we have three allotropes of carbon. We have diamond, graphite, and buckyballs or nanotubes. Properties of diamond. This is a covalent network solid. Carbons are bonded tetrahedrally. So this is, remember on the back side I said covalent has different kinds of crystalline structures and amorphous structures. So among the crystalline is the diamond, where each carbon is bonded to four other carbon atoms. Okay, so we call it a coordination number. Coordination number is 4 for diamond. Coordination number means that each unit is bonded to how many other atoms. Okay, in that crystal structure, each atom is bonded to how many other atoms. So for diamond, the coordination number is 4. That means each carbon atom is bonded to 4 other carbon atoms. Carbon are bonded to 4 in the tetrahedral form, like this. They are one of the hardest substances known because of a very strong covalent bondage. Okay, they kind of interlock each other, and that gives it the strength and the solidity. And so we use it to make cutting tools, polishing tools, and dental drills. And of course, diamond jewelry is also very important because it doesn't get stretched easily. It's very hard. They have high melting boiling point, 3,550 degrees Celsius of melting point, and 4,827 degrees Celsius of boiling point. So they are very, very, very hard. No electricity conductor because they have very strong specific crystal structure. It is not mobile. Particles are not moving around. Insoluble in polar and non-polar solvents, so like water or even hexane, or it's insoluble in both because molecular bonds are stronger than any other intermolecular forces. Okay, so the bonds within atoms is much stronger than the bond between this and the other one. Okay, so this is also a difference between a covalent bonding and a molecular bonding. In a covalent bonding, atoms within the molecule are much stronger bonded compared to the molecule-to-molecule bonding. Okay, that's a different discussion. Staying to the allotropes of carbon, the second allotrope is called graphite. You see they have hexagonal sheets of carbon atoms. Okay, and those sheets are held together by these intermolecular forces, London dispersion forces. They kind of float on each other. Okay, they kind of float on each other. Those hexagonal sheets. So since they can float on each other, they have double bonds. The double bonds between carbon, or we call it pi bonds or double bonds, they make them float on each other. And that's what makes them good conductors of electricity because of those delocalized electrons. They have high melting point. They're also insoluble in both polar and non-polar solvents. Their coordination number is 3. That means each carbon is bonded to 3 other carbon atoms. Okay, for diamond the coordination number was 4. For this one it is 3. That means if we know each carbon makes 4 bonds.
Has 2 double bond or 2.
It has 1 double bond. Right? Each carbon is making 1 double bond. So it's like this. Of course, carbon is going to make 4 bonds, but this double bond that is there is going to make them float on each other. So this is what this is where the delocalized come from, the double bond. So the forces they're holding each other by are in dispersion, one wall dispersion forces. They're not very, very strong with forces. Fluorine is a very unique reality. It's a allotrope that we recently discovered, in which the delocalized electrons are such in nature that they made this allotrope very soft. I can make it a ball. I can make it a tube. We have, I can bond a long chain of carbon 60. 60 carbon atoms are bonded together. So, and I can take that chain of 60 and kind of wrap it, roll it, ball it, however I want it. So we call it buckyballs. They're spherical, of course it's a ball, or I can make it nanotubes of a tube shape. So I can give it any shape I want. Both have very interesting properties. They're super strong. They conduct electricity. Why are they conducting electricity? Because again, those delocalized electrons, they have low resistance to any other to heat, and they have free radicals here. They have free electrons that can move around. So next is those buckyballs where you see each one is bonded to three again. Carbon atoms bond in units of 60 atoms, forming a structure similar to a soccer ball with interlocking six-sided and five-sided rings. Extra p orbitals, those double bonds are there, and that makes them conduct electricity again. They have strong covalent bonds, and they're also insoluble. So that's about it. I mean, as far as